Hi, it's me again. Um, so we have been talking about the period of a mass on a spring using this um, this document that you have, and it looks like this at the top. If it shows up, being very slow. There we go. That's what it looks like at the top. Um, and we found that the period of a mass on a spring using just energy, really, and this analogy with circular motion going around and around in a circle gives us the period of 2 pi times the square root of m over k. We'll do the same thing now with a pendulum so that we know the period of a pendulum. And we can use the same analogy of, well, we know that everything's an energy, right? And the energy is given by the, energy is the sum of the kinetic energy plus the gravitational potential energy. And that's delta PEG. And well, we have that we know that the delta H is ultimately what we have to find in order to find what our change of potential energy is. Now, the reason that we get a change of potential energy is because the pendulum swings left and right. And as it swings left and right, it also goes up and down by this delta H here. And that delta H is related to the length, obviously. We have the length here of the string. And there's also, that's going to be the same as the length here, going from here down to here. Because the length of the string doesn't change. And we know we've gone through some angle theta, right? That angle theta means that, since this is a right angle, that the side length here between this and this is given by L times cosine theta. So if we know that the whole thing is L, and this particular side length, the red bit, is L times cosine theta, then the delta H is given by L minus L cosine theta. Make sense? So we have L minus L cosine theta, and that gets put into here in place of delta H. And we can factor out the L, and we get mgl times 1 minus cosine theta. Now, I know, because I've seen a lot of these things, that 1 minus cosine theta is an identity. And that identity works out to be 2 times sine squared theta over 2. And I'll show you how that works in a little bit. First, I want to go ahead and put that in. So we have delta PEG is equal to mgl times 2 times sine squared theta over 2. Okay, and I'm going to do another mathy thing here in a moment. Since I know that our angles are small, we can use what's known as the small angle approximation. And that small angle approximation tells me that sine of x for a small x is equal to x for small x. Okay. So, well, what does that mean here? So that, I'm going to say that, well, our pendulum is swinging through a small angle. It's going only between 15 degrees and minus 15 degrees. So I can just replace this equals mgl. I should probably put the 2 in front of that. Let's put the 2 in front of that. Equals 2 mgl times, and then this sine squared theta over 2 just becomes theta over 2 squared. Now, you may be wondering where that comes from. So we have two things that we want to know where it comes from. A, we have this idea, we have this identity that's true, and then we have the small angle approximation. So let's hop over to Desmos here. I'm going to stop sharing. What's the best way to do that? Just go in here, and I will share Firefox. There we go. Cool. So you can see that we have, well, I've already graphed y equals 1 minus cosine theta on this Desmos thing. Let's go ahead and see what that actually is. This to me looks like it's going to have a squared term of a sine, because it starts off at 0 and it goes up in sort of a parabolic sort of direction in both directions. So I'm going to just type that in, y equals sine squared theta. Cool. All right, that already looks a lot better, right? We've got the we've got it going up in both directions. It looks like our period is too fast, so we're going to have to slow down the period. I'm just going to take that, let's put a space in here, and then say theta over 2. There we go, and the period looks about right now. But it's still not a high enough amplitude, so we need to multiply this by 2. So let's go ahead and put 2 in front of all that, and that looks like a perfect fit. So I haven't proven it, and I know Leonard wouldn't approve necessarily, but I have demonstrated that the 1 minus cosine theta is the same as 2 times sine squared theta over 2. The other thing that we wanted to demonstrate was the small angle approximation. So what I've done here in Desmos is I've plotted y equals sine theta, and you can see that's the red one. It goes up and down and up and down and up and down. And then some of you may know this from your math class. There is what's known as a Taylor series. It's an expansion where we say that if y equals theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, and so on and so on and so on, we will end up with with the sine function. This is actually equal to the sine function. I put a dot 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 here, which I don't know if I can do. Yeah, dot dot dot. That's going to equal the sine function. Can't do that in Desmos. I'll get rid of those. But if we just take the first term of that Taylor expansion, say y equals theta. Let's go ahead and plot that and get rid of the other one. See that y equals theta. Now we see that, in fact, y equals theta is a pretty good approximation for y equals sine theta for any small angle here. I didn't put this in terms of pi. Let's go ahead and change our y-axis, x-axis rather, to pi. That didn't work. Okay, never mind. I just labeled it. Step should be pi. There we go. Okay, cool. So we've shown that maybe up to about pi over 6, we've got a good approximation of y equals sine theta. All right, so let's go back. I'm going to stop sharing here, and then you can see my face for a moment. And I'm going to share back on this thing. Start button. Let's see if that works. Okay. So we have our small angle approximation. It's already been put in here, and we can make this equal to 2mgl times theta squared over 4. Okay, and then we know something else here. I'm going to use a different color. What's a different color? How about green? We'll go to green. This curve S, this curve here rather, is the shows how far the mass at the end of the spring moves when it goes through some angle L. And because we know that this is just thetas and radians, then we have S equals L times theta. So if we solve that for, let's just keep it in green for a moment. We solve that for theta, we get theta equals S over L. So let's go ahead and put that in down here. And that gives us 2mgl times S squared over L squared. And we still have that 4 in the denominator, which we should probably get rid of. Okay, so we can get rid of this L squared and that L. We can get rid of this 4 and this 2. This turns into a 2. And that turns into mgs squared over 2L. And that's delta PEG in terms of this, how far we've gone from the central point. All right, let's go to the next page here. Okay, now we know that conservation of energy says that delta PEG max equals KE max. So what we're saying here is that the farthest we can go in the left-right when we're swinging idea is going to give us only potential energy, gravitational potential energy, and no kinetic energy. So that's all the energy is going to be potential energy. And then when we're at the bottom, there's no potential energy. Well, there's no delta potential energy. So all the energy is going to be kinetic energy. So those two at their maximum should be equal to one another, which is the same argument we made with the mass on the spring. So let's go ahead and take this. What do we have up here? I wonder if I can copy that. You probably can. Last I select. Okay, I'm going to say copy. How do I copy? Copy. And then we're going to paste. I cannot paste. All right, I'll just write it down again. So what did we have? We had that delta PEG. Need to have that. Delta PEG is equal to mgs squared over 2L. And that's equal to 1/2 mv max squared. Okay, and this S is not just any S, this is S max. That's how far. Let me try that again. S max over 2L. 1/2 mv max squared. All right. Let's go ahead and cancel some of these things out. So we have 2 in the denominator, both sides. We have m, both of those. Oh, and one other thing we know is that S max is actually just the amplitude of the swing. So what do we have? We have equals G times A squared over L equals V squared, V max squared. Okay, now let's put that in terms of A squared over V squared, and we'll get to Y in a moment. A squared over V squared max equals L over G. Okay, and remember from before, when we were having the particle going around in the circle, we said that the period, here boxed in red, is 2 pi A over V max. So let's go ahead and remember that. Period is 2 pi A over V max. And that's just because we know the geometry of the thing, of the particle going around in a circle. So A over V max, A over V max is equal to the square root of L over G. And that means that the period is 2 pi times the square root of L over G, which is the period of a pendulum. So the period of a pendulum is obviously related to the length. I think you found that when you did your lab. You also probably, well, you didn't find. Pretty hard to vary gravity, at least in San Mateo. So it's also related to the gravity, which you may not have found, but it would have been interesting if you had. All right, so this is a useful a useful result, and you should be able to use this to finish your lab and to do the next problem set. Thanks very much. I'll talk to you later. Bye-bye.